Hello, good evening. So today I'm just going to talk just a few minutes about nanotechnology and nanotechnology in general. So this is for the digital assignment for physics. I am asked to do 15 minutes of the whole presentation, so I thought I just might as well jump right in. So nanotechnology. It's study into physics in the nanoscale level. It was first laid out in 1959 by the physicist Richard Feynman. Atoms, generally below the nanometer size in terms, when we talk about molecules or proteins, and they range generally in the nanometer spectrum, like that region generally. We generally deal with atoms, generally anything in the size of 1 to 100 nanometers, that's the range. In other words, it's 1 billionth of a nanometer, 1 billionth of a meter, sorry, and it's about 10 angstrom. For instance, fingernails grow approximately 1 nanometer per second. So, nanoscience. How do we define nanoscience? Nanoscience, in general, is the study of the phenomena and manipulation of materials at atomic, molecular, and macromolecular scales, where particles differ from large scale, basically. Nanotech is in a sense controlling the shape and size in the nanometer scale, and I'm just going to gloss over some of the theory that we really do know of. Electrons, when we talk about electrons, undergo quantum confinement. Shows quantum dots, remarkable increase in surface, decrease in size. Nanoparticles are about 10 nanometers diameter, 10% the surface of atoms. 1 nanometer size particle is about 100% the surface of atoms. So we just generally talk about it. So an example of this would probably be melting of Au, aurum, or gold particles. The size decreases. Variation in interparticle space and geometry also result in electronic properties. Small particle electronic state, not continuous size, decreases. Electronic band narrows, delocalized electrons transform to more localized molecular bonds, ionization potentials, smaller size, higher than bulk show in size, generally speaking. Alright, so how do we put it? So I think a common example for applications or problems that we face from nanoscale materials is, for example, the storage of hydrogen, especially like hydrogen in general. If we've noticed in practical engineering senses that once we try storing hydrogen in metallic canisters or tanks in general, we then realize that one big issue is hydrogen by itself doesn't leak directly, but over time you realize that, say, if you put 1 kilogram worth of hydrogen in a metal canister, you can check it back up in 1 week, give or take a few days, and you notice maybe about half the hydrogen has already escaped. The problem is hydrogen slowly seeps out of the canister due to the between the intermolecular spaces in between them. So what the general solution to that is you absorb hydrogen, or you store hydrogen in on metals. Basically, it's absorbing hydrogen onto metals as a practical solution to this. That's a common practical problem that we've solved generally with nanophysics. So the fundamental challenges in nanostructure materials are, there are many challenges, let's be real. Us as macroscopic beings, biggest concern is how do we deal with these materials in the nanoscale. So when we talk about materials in that sense, we can say the ability to control the scale of the system, the ability to obtain required composition, details such as defects, concentration gradients, etc., understand the influence of size of building blocks in nanostructure materials, and all of them are general issues that we face very much often. Synthetic procedures, yeah, and that is true. I myself come from the chemical engineering background that I've been learning chemical engineering, and this is actually very important to us, which is the synthetic procedures, like a gas phase, vapor evaporation method, reduction of metal ions, decomposition of organic metallic compounds and cluster complexes, metal atom vapor synthesis, metal vapor deposition into polymer, encapsulation in inert gas matrices, sol gel processing, so on. All these processes which we deal with tend to happen in the nanoscale method. If we're talking more, and to put it into more daily, what we face day to day is like when we handle like our devices, like my phone, which I'm recording this on, we realize that at the heart and core of all these devices is the SoC, or a system on a chip, and the most common one is, of course, the Intel chips, basically. And Gordon Moore, the founder of Intel, the development of integrated ICEs in general says that general growth rate in the industry, we can say that about the space on transistor generally shrinks by half every 18 months. What he means to say is the space required by one SoC, whatever space that takes, is halved every 18 months. So this trend's been successfully continuing for quite a while. I'd say about more than 2.5 to 3 decades. The problem is the current FinFET and the nanoset processes that we're going right now for general consumer level processes is about 40 nanometers, which, if you think about it, is very, very small. Like even the smallest components being much smaller than a single blood vessel, a blood cell in general, basically. So, and when he specifies about it, like Moore's second law also states, the cost of building a chip manufacturing plant doubles every 36 months. So, the problem with general technology nowadays is like keeping the price low, that it's accessible to consumers, but also making it profitable for the companies that are also making these chips. Because at the end of the day, it's private endeavor. You don't really see government or public, institutions trying to get into manufacturing of this, because it's more of a profit-oriented business. And it has been for a very long time. So while talking about this, we can discuss about the quantum well, the quantum dot, and in terms of quantum wire also. The quantum well generally dictates about the second dimension electrons, quantum wire generally 3D, and quantum dot is just the one dimensional. No reference about this. I'm just glossing over most of this because it's very time consuming, but I'd say there are many applications for nanotechnology in the future. We can say the nanonets, solar cells, sensors, touchscreens, all have their place in the current world, basically. And other applications, of course, we use a lot of nanotechnology every day, but we tend to ignore it, basically. General applications include sunglasses, like ultra-thin polymer coatings, scratch-resistant coatings, windproof, waterproof clothes, sunscreens, cosmetics, sports equipments, automobile fuel lines, nanotubes, cutting tools, nanocrystalline materials, washing machines, antimicrobial property, hydrogen storage devices, magnetic recordings. I mean, yes, even that point alone, basically, whatever we read and write on our hard drives or our SSD solid-state drives generally uses magnetic recording as a way of maintaining data. Now, of course, that's also an interesting issue because I'm not sure if many people have heard about this, but if you take a hard drive or an SSD through most metal detectors, there's a very strong chance that you might be able to corrupt your hard drive because the magnetic resonance that takes place in between it starts scrambling the data, which leads to corrupt files in the long run. There are a host of disadvantages as well. We talk about the advantages of what nanotechnology has been like its impact on our day-to-day lives, and we say that there's a lot of advantages, but it's not been without disadvantages. For example, like it is high-cost technology. Like this is a very bold, how do you put it, field to invest in. Considering like current day applications are limited, but the future aspects are wide. They have a huge amount of future potential. So, talking about it, they have high cost. Some nanoparticles burst into flames. I really can't really discuss about that. That just happens apparently. Some nanoparticles enter the body easily. That is actually true. Dealing with nanoparticles, you have to understand that your skin is definitely not like skin pores are definitely bigger than nanoparticle size. So dealing with it in that sense, like you have to understand your fingernails, or like the fingernails we have, grow at about 1 nanometer per second, and we really don't see that anywhere. And the problem with that is, while we discuss about it, to think about it, if you drop a small vial of something that's poisonous and happens to be in the nanomaterial scale, or we can say nanobots or nanites, they easily enter the body. So biowarfare will definitely gain a huge boost in this sense, and that would, I mean, in the wrong hands, let's be real, this technology has the potential to do a lot of harm. There's a danger to brain and vital organs, and that is true. Actually, there was a story a couple of years ago that dealt with, for us from the chemical perspective, there was, I believe, a scientist that was handling organic mercury. Right. Now, organic mercury is very, very lethal. If like you make a small contact on your skin with organic mercury, there's a good chance, unless you amputate that said part of the hand that came in contact with it, you generally die. And that has happened to, I think, one scientist for an undisclosed company was handling organic mercury, and she got a bit of it on her glove. Basically, she was wearing one glove over another protective glove on top of an additional, like three layers of gloves, and she thought she'd be fine. She just simply washed it off. 8 months later, she was sent to the ICU, the intensive care unit, where she was pronounced dead within a week. The reason being was mercury poisoning. Apparently, organic mercury attaches itself to lipids, so your fat cells, and it kills you very, very painfully over time. So she had a very slow, painful death. And there's no cure for mercury poisoning. It's just generally the easiest way to solve it is if you have some mercury that fell onto your hand. The most painless way is actually cutting off that part of the hand, amputate it, and hope for the best. Generally. Carbon nanotubes, while we're on the same page of this, CNTs, were created by Sorinio Ligirna. I'm assuming he's Japanese. Made from graphene plane, single or multi-wall layer. Very strong, flexible. Carbon atoms are hollow cylinder. Ends closed by semi-full ring, and different forms by armchair, zigzag, Cairo tubes. The general way that these, basically, a full ring is basically a Buckminster full rings, the buckyball, basically. They were generally created by the vapor deposition method. He realized that if you were to vaporize carbon atoms, they would generally attach themselves as this very structured form. Some of the nano examples included inorganic nanowires, protein nanotubes, nano in gene sequencing. The CNTs also have plenty of applications generally, but I think discussing about it, I think Young's modulus for over 1 TPa versus 70 GPa for aluminum, 700 GPa, for carbon fiber, and if you compare it, actually, the actual carbon fiber strength for these CNTs is very much greater if you compare it with generally to steel, to iron, to any other construction materials that we've used so far. And we can actually say the maximum strain is about 10%, much higher than any other constructor material that we've used, basically. And CNT has wide variety properties. They have very high current carrying capacity, which wouldn't be a surprise. Electronic dipoles are everywhere. Excellent field emitter, high aspect ratio, and small tip radius for curvatures. Electrical conductivity is 6 orders of the magnitude higher than copper. And that is a very conductive material, if you think about it. Electronics have, I believe CNTs have very huge applications in electronics because they pave the path for high conductive pathways. Like, unlike using other conductors like copper, which would just be slow, you could use this in many fields like quantum wire interconnections, diodes and transistors for computing, capacitors, data storage, field emitters for instrumentation, flat panel displays, terahertz oscillators, and much more. They have such a wide variety of applications. And they do have a huge amount of applications, though. Like, we can say that they are body armor, spike suits, it could be filter membranes, they could be radiation shields, and that actually was also pretty important because up to now, your best way of shielding yourself from radiation was 4 inches, I believe it was 4 inches, of thick lead, and hope for the best, assuming gamma radiation doesn't get to you. But then again, gamma radiation actually would be the one that penetrates the least, but it is the most dangerous of said types of radiation, alpha, beta, and gamma, of course. There are many other applications. Honestly, we're just dealing with applications. There's biomedical applications, there's nanoscale reactors, ion channels, batteries, fuel cells. Of course, lithium-ion batteries being replaced by better nanoscale replacements are definitely what we look forward to. I mean, generally, if you think about it, our biggest weakness in electronics these days is our inability to store charge. Like, you have a phone, you do have to recharge it at least once or twice a day. You have a laptop on battery, pray to God it lasts for more than 4 hours. So we do have to deal with those as detailed issues because they are issues that we face the most. Because if you take electronics in general, that's your weakest point. You improve on that, you generally improve the system as a whole. Biosensors, nanotube sensors, and a lot of them. CNT synthesis, of course, as we discovered, was CVD, or chemical vapor deposition method, and was ideally patterned, of course. I'm not sure if the technology is patented, but I assume it is such. And that generally talks about CNT synthesis. I believe my lack of time prevents me from jumping into more details about nanophysics in general, but hopefully I'm seeing if there's anything else I can add to this. I don't think there's much I can add to this. CNTs in general, like actually nanotubes in general, basically. And yeah, I don't think there's much over here. We have to point out that any substance we take from the macroscopic scale, we compare to nanoscale, definitely has a change in properties, because we know that like atoms, when they bind together as molecules, already have different properties than their atomic counterparts. So catalytically would be different, electrically would be different, magnetically, mechanically, optically, sterically, and they all have variations everywhere. So I think that's all the time that I have, basically. So thank you for listening to me, and I've just glossed over a very large amount of topics. So hopefully I hope that this video was informative, and I conveyed a message directly. I talked about nanophysics because I generally thought that the other topics would probably be a bit more arduous or a bit more harder to explain. I mean, I would have loved writing it on a piece of paper and showing it as well, and editing the video generally. It is part of the digital assignment, but I simply didn't have the time, and nanotechnology is the easiest way of explaining it, because it's just fully theory. Let's be real. So thank you for taking the time to watch. I have only rendered the video in 720p, so sorry for any discrepancies. And thank you for watching me, and have a nice day.